Hello, everyone. I'm so excited to finally see everyone in person. And today we are going to discuss how to evolve your Kotlin API painlessly. So by evolving, I of course mean like adding new cool features, adding new functions, classes, and so on. My name is Leonid Startsev, and I'm working at Kotlin libraries team at JetBrains. So to understand how to do this painlessly, we of course must first identify where the pain is. So let's start with talking about compatibility. So a lot of people may think about compatibility in this way. So let's say we have some library A that has some version like 1.5.1, and we have an application that depends on this library. So what happens if we update, if library author releases new version, say 1.6, that has some incompatible changes, like they have deleted a method or class or so on. So application developer sees some red code, some unresolved reference, and so on, and they need to perform a migration. This is maybe quite time-consuming, but it's not nothing out of the ordinary. It's a regular job. And then, like we developers, it is what we do, like editing code, committing code, running code, and so on. So you may argue that this is a part of the application developer's job. But this is not the case. And in real life, it is quite often you may encounter a setup like this. So you have a library A that gets into the application dependencies not directly but as a transitive dependency. So in this graph, we have a library B and library C that both depend on this library A. So what happens if application developer updates to a new version of library B that depends on a new version of library A that, as we know, have some incompatible changes? So library C, if we use default gradle resolution rules, gets into its class path this new version of library A, but it's not ready for it. It may need to call this deleted method or something else, and it simply gets broken. It can't no longer work normally. So application developer sees now some strange errors like no such method exception or no class defound error or incompatible class change error or something else. And these errors can be quite confusing even for experienced developers. But the real problem is that application developer can't fix this error. Its problem is not in their code. So it turns out that maintaining backwards compatibility is a part of a job for a library author, because application developers can't do anything with it to fix this. So today we'll be talking about Kotlin JVM. Of course, Kotlin JS and Kotlin native also have some nuances with it, but this talk today is quite short, so we can't fit it can't fit it today. And we will be talking from a point of view of a library developer. But this doesn't mean that you have to have an actual open source library. It can be as well closed source, or can be just a module in some complex in-house system you have at your job. And generally, anything related to the dependencies between jars that are deployed and released separately can also be related. So we are talking here mainly about backwards compatibility. So as you might have guessed, this is a property when clients who expect old library version in a class path still can work with a new one. And it can be easily broken, for example, by removing a declaration from a library. There's also, of course, a notion of forward compatibility, but it is usually discussed when we talk about data storage and like data schemas, like database schemas, protocol buffers, and so on. So it's not that related to the code. What is related to us is these types of compatibility. So it can be functional, and can be binary, and it can be source. So let's break down each one. Functional compatibility is simply a property when the function continues to behave like it used to in new versions. So for example, if you had version 1.5 and fun feed in there said you fed the tiger, and in version 1.5.1 this function says the tiger ate your fingers, well, it is a completely different behavior. This is not what clients expect from it, and well, this also may break some things for someone. So what you should remember about this, that you shouldn't introduce like major changes to your functions, to how them behave, unless it is absolutely necessary. It can be necessary, for example, fixing a security bug, but generally don't do this. So source compatibility is pretty self-explanatory. It is a property when application developer can compile their code using one version and can't no longer do it with a newer version, for example, because of unresolved reference or other compilation errors. And the binary compatibility is when application can no longer run using the new version of a library, and you might get some strange errors. So what we should remember about it is that this situation can happen even if the developer does not use problematic declaration directly. So as this example with transitive dependencies, so even if we do not use problematic declaration, but our library C uses it, we are doomed. And the rules here are defined by Java virtual machine, because we are running bytecode, and it depends on how calls in bytecode works. So what do we want as a library authors? We want full functional compatibility without like modular bug fixes. And backward source compatibility is highly desirable, but it's not that necessary, because in the end, if some code is read, we can just perform some migrations, and it will be OK. But backward binary compatibility is a must-have property for any stable library, because if it's not maintained, we can bring a lot of pain and troubles for people we may not even know. So you may think that source compatibility can be equal to a binary one, because it is often true in the cases like removing a declaration or changing method parameters list or adding an abstract method and so on. All of these things break both source and binary compatibility. So raise your hand if you think that they are the same. No hands, great. So indeed, they are different things. So let's try to break source compatibility and save binary one. It's pretty easy to do. Let's look at this function that is available in Kotlin standard library, and it's called join to string. So it has a lot of parameters with default values, and one of them is limit. And let's imagine we have just decided to rename it into something nicer, like max items. And because we know that bytecode doesn't store parameters names, we may think that this is a binary compatible change. And indeed it is. But when we call this declaration with using a named parameter syntax, like in this example, if someone used a limit parameter explicitly, this code can no longer be compiled. So we broken source compatibility, but saved the binary one. Now let's try to do the opposite. Let's try to break binary compatibility without noticing it. Unfortunately, it is easier to do this. So if we had a function jump with a default parameter length, we may try to add a new parameter to it, also with a default value. So now we have jump from length and height. So we know that if somewhere in our code was a call to jump function, we do not need to change this calls, because compiler will insert a new value for a new parameter automatically. But if we compile this code and check what's happening in the class file, we can see that the function signature has changed because we do not longer have a jump function that accepts one integer argument. We only have jump function that accepts 2 integer arguments. And the way the Kotlin compiles function with default parameters doesn't affect binary compatibility in any way. It just adds a bit mask and some special marker object. So the binary signature of this function has been changed. And it also can cause problems. Another example is when we want to narrow or expand type. So if you had a function, reminder7, that takes int and returns number, if we change return type to int or parameter type to number, it will likely be source compatible because changing call sites is not necessary, as these types can be coerced into one another. But because the function signature has been changed, it is a binary incompatible change and can cause no such method exception. So in the end, you can get yourself in a situation like this, when your code is green and when your tests are green and you haven't even changed them. But people say that the new release is awful because it broke some transitive dependencies, broke some applications, and generally no one can migrate to this new version because it is broken. So preserving source compatibility while breaking binary at the same time is the most dangerous type of changes, and you should avoid it. So now, when we identified where the problem is, we can talk about how to track binary compatibility and how to avoid making such dangerous changes. So how can we track it? Well, first option is to just remember by heart what bytecode Kotlin compiler produces. So if we know that we shouldn't add any new parameters with default values, we shouldn't add new other methods and everything, shouldn't change return types. So we may avoid this, but this is costly. This requires a lot of experience, and you should ask yourself every time if this change is compatible. So another option is to write integration tests. You have to spend some considerable amount of time setting up this scenario with transitive dependencies. But once you have done it, it will likely save you from releasing a broken version and report you the errors that you can get. And the other possible option is to compare jar files, because this problem also affects Java and is generally widely known. So, of course, there are some tools for Java that can help prevent it. For example, JAPI CMP that compares signatures into given jar files. And you can also use them with Kotlin, because Kotlin compiles to the same bytecode. So it is possible. However, we as a library team can offer you a better solution, which is called Binary Compatibility Validator. So it is a Gradle plugin that you can include in your Kotlin project. It can be a JVM project as well as multi-platform project, but it still works only for JVM part. So when you include this plugin to a project, you can see that there are 2 new Gradle tasks. One of them is API dump, and the other is API check. So let's break down what each of these tasks do. So if we invoke Gradle API dump, we can see that in our project there is a new folder called API, and there is a file in it with the .api extension, and it is named as the same as the project name. So what's in this file? If we had a declaration like this, very simple class, tiger with fun meow, so the API file will contain the API for this class and for all public classes in your project. So what can we see? We can see every public function and every public class. And for example, we can directly see that we have public fun init, and it is quite easy to forget that public classes, like this one, also have a default constructor without parameters, but it is still another public function. So by doing this, we have just bootstrapped the validator. So to start using it, you need to first add a plugin to your build script, then generate a baseline.api file with API dump task, and you should add it to your version control system. So how to use it in the daily routine? So imagine we now have did some refactorings, and we added a loudness parameter to our fun meow. And as we just learned, we know that this is a binary incompatible change because it changes signature. So when we invoke API check task with this change, it gives us an error. So what is it saying here is basically, hey, I've just taken the dump of your public signatures and I compared it with the file you have in your version control system, and they're different. So please do something with it. And it fails the task and it fails your build because API check is a part of Gradle check. So to use validator during development, you should follow these simple rules. So if your API changes are unintentional, then you are saved because API check will fail your build and you will get informed by your CI or by something else, whatever you use. However, if API changes are intentional, then you should do the following. First, you should update golden API file with API dump and commit these changes. And then you should just send it as a part of review. So the side note here, the binary compatibility validator is a pretty simple tool. So it doesn't answer you when your API is compatible or not. It simply says if it is changed. But reviewer can use also some heuristics, like if it API dump, if changes in the API file are only additions, so we have only added lines, then API is likely compatible because we haven't deleted or modified anything in it. But if there are changed or deleted lines in this API file, in this commit, so it requires attention because the new API is likely incompatible with the old one. So we use this tool in pretty every Kotlin library, so in serialization, in coroutines, and stdlib, and it has proven itself to be really useful. So another tool that we use called explicit API mode. So why is it needed? We all know that by default, Kotlin declarations are public. But not everyone knows that some time ago it wasn't like this. So in pre-1.0 versions of Kotlin, and some milestones version, the default visibility was internal. But after some consideration and after some studying of large Java code bases like Kotlin compiler and IntelliJ, the designers of the Kotlin decided that because public is used so often, it makes sense to make a default Kotlin visibility public one. And this is indeed quite handy for application developers, but not so great for library developers. Because it may cause some confusion. Like in this situation, so if you have our fun meow with loudness, now let's do some refactoring to it. So we take string literal meow and extract it into a separate function called meow once. So then we commit these changes and send it to the review. And what reviewer sees when they look at this comment? So we know that funmeow is likely public because we already have it, and we can change visibility of public functions just like that because it breaks compatibility and so on. So it is likely public. But what about a new function, meow once? Is it public by intention? Was it intended to be a part of a public API? Or is it just an implementation detail that should be private, but the author of commit forgot to add the private modifier? We don't know this as a reviewer, and so we should write a comment. I'm sure this should be public, send it, this delays the review, adds to the comments, and so on. So in general, it's simply easy to forget the modifier you wanted to use, and it's not clear for the reviewer. So in explicit API mode, however, you are forced to write an explicit visibility for all your declarations. So if you write just one mel once using the explicit API Kotlin compiler mode, it will report us an error that visibility must be specified, and thus saving us from danger of forgetting visibility modifier. Another part of this mode is related to type inference. So Kotlin compiler has type inference for variables that we all love. And it also has type inference for functions that fit into one statement, like this one, when you write mel once equals string literal, and Kotlin compiler can infer that a return type of this function is string. But what if we accidentally change an inferred return type? For example, we used subsequence instead of substring for some reason, and now the return type of this function is also changed. And we may even do not notice it because, well, we haven't changed this exact line. It can be the other function in the implementation that have changed. So if we already have a binary compatibility validator in this project, it will, of course, report us an error about that this function signature have been changed. So it's incompatible, so do something with it. But with explicit API mode, we don't even have to wait for the build to fail. Because explicit API mode also forces you to use explicit return type for public functions. So it is no longer possible to use an inferred type. You should always write it explicitly. But for private functions, you can still use type inference. So to sum up, explicit API mode saves us from accidentally public declarations and saves us from accidental return type changes. And of course, all diagnostics have IDE quick fixes. So fixing these issues is just a matter of several keystrokes. So we also use it in almost every library, I think, and is highly recommended. So if you want to enable explicit API mode in your project, everything you should do is to just call explicit API in the Kotlin configuration block, or use assignment is explicit API equals to explicit API mode.strict. So this setup will give you compiler errors on the issues I've showed you, like missing explicit visibility and explicit return type. But if your project is quite large and you are afraid to introduce so much compilation errors at once, you can use warnings mode. That will obviously emit you warnings instead of errors for the issues like that. So, and the last setting I recommend you to use is simply all warnings as errors. It protects us from things like unused parameter, unchecked cast, extension shadowed by member, and so on. And sometimes these warnings can affect your public API, so it's better to use all warnings as errors. So to enable it, it's possible to use free compiler args, but such settings sometimes is a point of controversy because a lot of people say, like, oh, I'm experimenting when writing my tests. I don't want compiler to report any unused local variable I have to use in my test because I want to check something, and so slows down development and so on. So what I recommend you is to turn all warnings as errors mode only for production sources. So if you take your compile Kotlin task, you can enable all warnings as errors there, and for compile test Kotlin, leave this setting disabled. So by doing so, you can freely experiment in your test sources, but your production sources will have pretty much stricter rules. So to sum up, these three techniques are actively used by all Kotlin X libraries, and they are all pretty useful, so I recommend you to try them. Yeah. So we've discussed a bit how we can track changes in our API, but how do we make these changes, especially changes related to removing something when some function no longer meets our purposes or has some unfixable design bug? We still need to somehow prevent it from being used in the future. So how can we remove something, and can we at all? So, well, we know that before deleting something from the library, we should first deprecate it. And for example, in Java, if we had some class tiger with fun meow, we can think about a bit and say, hey, tigers don't meow, they roar. And so we need to deprecate our fun meow. Oh, sorry, public void meow, this is Java. So we deprecate public void meow and introduce new public void roar. But the question is, how do we communicate this change to our users? How to tell them they should use a new function? So we can write a Java doc that says that has some special tag in it at deprecated, and say the reasons for deprecating these functions and what should they use next. Yes. And so if you use IntelliJ, IntelliJ is smart enough to parse the Java doc. So it gives us this nice tooltip, which says meow is deprecated. But the reason for deprecation is only like this deep down below at the end of tooltip. And the most visible message, the first message in the tooltip, simply says that meow is deprecated without apparent reason. And sometimes we can get a replace with action here, but this really depends on what is written in Java doc and how was it successfully parsed by IntelliJ or not, and generally is not very reliable. So, in contrary, in Kotlin, we have separate Kotlin.deprecated annotation that has more parameters than Java deprecated. So we have message, which is mandatory, by the way, and we have replace with, and we have level. So how to use all these tools to make migration for your client smoother. So naturally, we don't use any deprecated tags in kdoc because it doesn't have any. So we simply leave our kdoc as is and say that this function is now deprecated with a message stating the reason. And we can provide some replacement right there. So as you can see, I wrote deprecated, tigers do not meow, and replace with roar. So now what client of this Kotlin library sees? So they see that the meow is deprecated, and the reason why is it deprecated is stated directly after this deprecation message. So it is more visible to user. It is also visible by default when you do a Gradle or CLI build, in contrary to Java, which doesn't print these messages until you specify -xlint deprecated. And of course, we get all actions. So we have replace with, or we even have replace usages in whole project. So if it is a simple replacement, user can invoke these actions, and by doing this, they can migrate very smoothly and very fast to your new API. So the last parameter is deprecation level. And as we know in Java, all deprecations are warnings by default. And we also have default deprecation level warning, which is a regular CLI or IDE warning, which turns into errors with overrunning as error settings. But you know that a lot of people do not care about warnings and do not pay any attention to them. So if you really want your users to stop using deprecated decoration, you can use deprecation level error, and it is a compilation error always. So it is no longer possible to call this function anymore at all. However, there's also a third deprecation level that is called hidden, and it is very interesting. So when you mark your declaration with deprecation level hidden, it becomes almost invisible. It is invisible for auto-completion, it is invisible for Kotlin and Java compilers, but it stays in the class file and the ABI of your library. So by marking a declaration with deprecation level hidden, you're essentially deleting the function without actually deleting it. It reports unresolved reference, and you can no longer compile code that calls this function. But in case your library gets some transitive dependency to the old client, it still can work correctly with it, because it is there in the jar file. It's just invisible. So it is a very useful tool, and all functions that Kotlin has ever deprecated and removed, they're still in the Kotlin starter library. They're just hidden. So you can be sure that your old code may still work. So naturally, using these three levels, we can form some kind of deprecation cycle. So when we want to delete something, we should first deprecate it with warning, then deprecate it with error, and finally hide it. And the question is when to raise this level of deprecation. So answer is, it is defined by your compatibility policy. For example, Kotlin has the following compatibility policy. So if you had some declaration in Kotlin 1.n, then in 1.n+1, it is deprecated with warning. Then in 1+2, it is deprecated with error. And in 1+3, it is hidden. And in 2.0, we theoretically could delete all these hidden declarations. But don't worry, we won't do this. But it is possible if you adopt this scheme to you and say, oh, I just want to delete everything. So you can have a policy like this or have a different policy. So the key takeaway here is that it should be sensible and it must be communicated to your users beforehand. So make yourself a file like compatibility.md in your GitHub repository or somewhere else and say that we use the following policy. So we've discussed a bit about deleting functions. And now I want to focus more about evolving and adding new functions and why it can be not as simple as you might think. So, as we've just learned, the one library may have different flavors of API. So we know that there is a stable API with some reasonable guarantees. We know that there is a deprecated API. There also may be an internal API which is public for some technical reasons like multimodal dependencies or so on. And we also may have an experimental API. Why we want some API to be marked as experimental? So for experimental API that is fresh new, we may have, for example, a different compatibility policy or room for semantic changes. Because when you create a new function and release it, you may get some feedback about it, like, hey, there's a parameter missing, so can we add a parameter to it that will change its behavior or like accept additional data and so on. So we may want to evolve this new function quickly based on user feedback. But if it's stable from the start, we can't do anything with it except deprecating it and introducing a new function with a different parameter list. By marking something experimental, we say that we can break it, like add a new parameter. But by doing this, we can evolve much faster than with a stable API. So how can we mark something as experimental? There is a special tool for that in Kotlin. It's called opt-in annotations. So in Kotlin std.lib, we have the following declaration. The public annotation class requires opt-in, and it has parameters very similar to the deprecated one, because it is also a way to mark up API. So we have message and level, which is either a warning or an error. But this time, it is a meta-annotation, so it has a target of annotation class. So when you want to make an experimental annotation, for example, in std.lib, this is experimental unsigned types. You should mark this annotation with requires opt-in, with the desired level of warning or error. And for example, unsigned byte array is marked with experimental unsigned types, which is marked with requires opt-in warning. So now how does use side of these experimental declarations looks like? So imagine we are writing a library that depends on Kotlin stdlib and does something like process time series. And we want to use a time mark and unsigned byte array. So because unsigned byte array is marked with requires opt-in warning, we have a warning reported here on usage of this declaration. And because time mark is marked with experimental time, which is marked with requires opt-in error, we can see a compilation error here on the usage of time mark. So what can we do with it? Well, the most simple and straightforward way is to propagate these annotations further. So we mark our process time series with experimental time and experimental unsigned types. And we get rid of these warnings or errors, but the user of our process time series will get them instead of us. So it's pretty easy to understand the reasoning behind this. Because imagine if a time mark is deleted from Kotlin standard library at some point of time. It means that our function, process time series, is also broken, because it can no longer be called or can no longer work properly, because time mark is deleted. It means that we depend on this experimentality of a time mark declaration. And this process time series cannot be stable because the corresponding time mark and ubyte array are also not stable. So we should propagate this experimentality to our users. The other way is to, you might want to opt into these annotations. So if you have some private fun or any fun, you can use opt-in to these annotations. So it just says that I accept the risks and understand that these declarations are experimental and may get deleted, but I want to use them anyway. So it also gets rid of the warnings or errors, but think before doing that in your library, because you don't get any warnings. But if this private fun preprocess is used in your stable API, it will still be broken when time mark or ubyte array changed or deleted. And you can't notice it because you've essentially suppressed the warnings about experimentality. So opt-in is mainly, again, for application developers. So to sum up, always prefer propagating over non-propagating. So use propagation when experimental types are part of your public declaration. And if experimental declaration experiment usage of it is an implementation detail, then also propagate if you can't control it. The exception is you can opt in into the experimental declaration if it is yours experimental declaration. So for example, in Kotlin serialization, we have experimental serialization API, and we can opt in into it in some of our implementation details, because we know when this API is changed, we know how to perform migration, and so on. So if it is your own experimental annotation, you can opt in into it. And do not use module-wide opt-in that suppresses the warnings for the whole module, because you may accidentally just forget about one. So it is also an option for application developers. So a side note, whether you should use one experimental annotations or multiple. In Kotlin serialization, for example, we have only one experimental serialization API, and we mark every new function, every new class with it. So it's possible to have only one. In Kotlin coroutines, for example, there are two of them, the experimental coroutines API and flow preview, because flow was a big separate feature that wasn't depend on experimental coroutines API, and it had some own evolution path and wasn't really related to it. So, and in Kotlin stdlib, we have various different flavors of experimentality, like experimental time, experimental unsigned types, experimental stdlib API. So reasons behind this is that these are, well, completely different functionality, and we may want to drop experimental time and promote unsigned types to stable at the same release. and so on. So in general, try to make an experimental annotation for every new large parts of functionality, but you definitely shouldn't invent a new experimental annotation for like every new function you add or something like that. Just use the big one like experimental serialization API. So to conclude, as we just discussed several different flavors of the API and several different states, we can naturally come to something that I call a declaration lifecycle. So when you add a new function, you can add it as an experimental in the experimental stage. In this stage, you can quickly gain user feedback. You can quickly make changes to it to form its shape and to understand what users of your library do want from it. So after some time with experimenting, in some point of time, after the minor release, for example, you can choose whether you want to promote this function to stable or whether you want to delete it because it wasn't like really useful or because we've discovered some design issues or for any other reason. So while the library is in stable state, you can do some bug fixes to it, you can like improve documentation and so on, but you can't really change this function in any major way. You shouldn't really change its behavior, you shouldn't change its signature, so it's kind of frozen in time. And if at some point of development, you've discovered that this function no longer meets your purposes, it is obsolete, or it contains some unfixable bug, or something else, you should deprecate it. And gradually, by raising a deprecation level, you can eventually delete it. So that's what's all from me. So I want to say two things before the end. So the most of the topics I've covered today, they're also available as a part of our API guide, which is brand new and was released several days ago. So it is accessible with this QR code or in koto.in/API guide. And yes, I think we don't have much time for questions and answers, but I'll be available at Kotlin booth in Kotlin Libraries office hours, which is, I believe, at the coffee break after the next talk. And also we have quite cool demos about Compose multi-platform at our booth, so come by. So thank you, and don't forget to vote. I hope you enjoyed today's talk.